Hello and welcome to this movie about field math. Fields are like vector spaces, but now have an element called 1 and a reciprocal or inverse for every non-zero element of it. This gives us some extra things to play with and some more interesting things to prove. Here are some of the variables we'll use. A and B will be representations of 1 in one of the proofs, while 1 is an element of the field and not just a scalar that can be multiplied by an element like in a vector space. So 1 will be represented by the number 1 in most of the proofs. It will be colored blue so that it can stand out as being a special element. 0 is also an element of the field and will be represented by the number 0, and it will not be represented by z like in vector spaces because no confusion can occur between the element 0 and the number 0. The negatives of a field element will be represented by n, or n with subscripts, and be colored magenta. The reciprocals will be represented by r for reciprocal, and r with subscripts, and also by s. In the case of a double reciprocal, which is the reciprocal of a reciprocal, sx will be used. These proofs will be set out like in vector spaces, with the first expression undergoing a series of transformations until it becomes the expression that it was supposed to be proven to be, making it look very neat and tidy. We can also use theorems that were proven for vector spaces. There's only a very slight difference between the proofs for fields and vector spaces, because both zeros are elements of the field and -1 is also an element of the field. I'll just quickly show you the zero proof. It's identical to the vector space proof in every line, except for this line where we add 0 and 1 together to make 1. Since 0 and 1 are both elements of the field and not numbers, then the property of zero axiom has to be used. And likewise for the negative proof. It uses the property of the negative to add 1 and -1 together to make 0. Since by definition -1 is the negative of 1, all three of these numbers have equivalent elements in the field. Now we can use these theorems to prove other theorems. Now we'll prove these two things, like that there is only one element that's a 1 for each field, and there is only one inverse for each non-zero element in it. Starting with the proof that there is only one element 1, we'll define A and B to both be elements that are 1s in the field. It is possible that there are two 1s in a number set. We'll start off with A, and using the property of 1s, it is equal to A times B, since B is a 1. This expands the expression. And then use the property of 1s for A, leaving B. So the proof is completed. It might be a bit hard to see it. A times any other number like u is u, so A times B is B, and B times A is A. It's a very short two-line proof. Notice how similar it is to the only 1-0 proof for vector spaces. It does follow the same logic. Here is a proof that there is only ever one inverse for any non-zero element. Here we'll define our variables. U is any non-zero variable in the field we can have. 0 has no inverse. R and S are the inverses of this variable U. We have to show that R must be equal to S. Starting with the first inverse R, we use the property of 1 to expand the expression. A has already been defined to be 1 in the previous proof. We expand this expression again using the property of inverses, for the second inverse S in particular. Now we use the associativity of multiplication to swap the brackets. This is a very important step because now it will simplify into something entirely different. Then the expression is simplified using the property of inverses for the first inverse, this time called R, leaving this expression containing the second inverse called S. This expression is simplified again using the property of 1 to become equal to the second inverse called S. So the proof is finished since R has been shown to be equal to S. Now to prove some more complicated theorems, starting with this one. It looks like it's easily proven with common algebra. Notice that x must be non-zero. We'll let this variable Rx be the inverse or reciprocal of x. We'll colour it magenta so it will stand out as being special and can keep track of it. It does exist since x is non-zero. Starting with the first line of the actual proof, we use the property of 1 to expand the expression. We'll use the property of the reciprocal to expand it again. Now we'll use the associativity of multiplication to swap the brackets. Now we'll use the fact stated in the theorem that xy is equal to xz. We say that it is given. We'll swap the brackets again. We'll use the property of reciprocals to simplify the expression. And we'll use the property of 1 to simplify the expression again to be z. This finishes the proof of this theorem. Now to prove this very obvious theorem. We'll assume that x is non-zero, because y could be any number if x was 0. So x has a reciprocal. Starting with y, we'll expand it using this axiom. And then expand it again using this axiom. Then swap the brackets using this axiom. Then at this strategic step, we use this property circled in the theorem to simplify the expression. Then we'll simplify it to be 1 using the property of reciprocals. So now we've proven the theorem. Now to prove this obvious looking theorem. This would be easily done in high school algebra, but not in field math. We'll start with y and expand it to be 1 times y. We'll expand it again to be this. We'll swap the brackets using this axiom. In this important step, we use the fact that xy is equal to 1, as given in the statement of the theorem. And we'll simplify it to become the reciprocal. Thus the theorem is proven. And now for this double reciprocal proof. Sx is x reciprocated twice. It must be equal to x according to the theorem. Starting the proof with Sx, we expand it using the property of 1 axiom. Then expand it again. Then swap the brackets. And now here's the strategic step. Since Sx is the reciprocal of Rx, then they must multiply together to equal 1. And the expression simplifies to be equal to x, which proves the theorem. And now for this inequality. We can prove this more easily by proving it's contrapositive. And so there are two cases. Either y is or isn't equal to 0. If it is 0, then the theorem is already true for this case. If y isn't 0, then we must prove that x must be 0. So we start with x and expand the expression. And expand it out again into y multiplied by its reciprocal. Notice that y does have a reciprocal because y is non-zero. Then we swap the brackets to gather y and x together. Then we use the commutativity of multiplication to swap x and y. So now x and y are multiplied together in the correct order, so as to set them equal to 0. because it is stated that xy is equal to 0 in the contrapositive version of the theorem. And now, using the theorem that 0 times any element is equal to the 0 element is used. We've already proven it for fields before, being slightly different for vector spaces. So now the theorem has been proven. Now to prove this theorem that multiples of the numbers negatives are equal to this. Starting with the negative of x times y, we expand it using this theorem that was proven for fields during this video. We use the commutativity of multiplication to swap x and minus 1, and use the cross multiplication sign since it goes in front of a number. Then we swap the brackets using the associativity of multiplication. Then we use this multiplication by minus 1 theorem a second time in this proof, so as to simplify the expression. Then we swap x and ny using this axiom to get them multiplied in the correct order for more precision. And so we've proven the first part of this theorem. Now to prove this second part of the theorem, so we expand it out again. And so we swap the brackets using this axiom. And we simplify it using this theorem a fourth time in this proof. So this completes the whole proof. And now to prove this last theorem, which looks very obvious. We expand the expression using this minus 1 theorem twice in the same line. And we move the two minus 1s to be next to each other, but in separate brackets. We slowly try to manipulate the expression so that the two minus 1s can be multiplied together. And yes, there are quite a few steps to do it, but now they are next to each other. And now we multiply them together to make 1. We invoke the property of 1 to simplify the expression so as to complete the proof. I hope that this movie has helped you understand how to prove theorems in math fields.